there's not a lot that you're going to have to write down today. You have to decide what's important, what goes down on paper. First of all, if you already know what I'm saying, you haven't memorized, you just, it's not even something you have to pause to think about. You already know it, don't write it down. The notes are for you, not for me. They're to help you prepare for quizzes and tests and so forth. So that's your first check. Then you have to ask yourself, is this the kind of thing that sounds like it could be a test question or a quiz question? Am I likely to see this again? Typically, if a teacher takes time to make up a presentation they're showing up on the screen, it's probably something that you're going to see again. Maybe not everything that's up there, but a lot of it. And you have to figure out what's important, what's not. And do I already know it before you write it down? If you get a slide that has a whole bunch of stuff written on it, and here, it's probably a good idea to just pause before you start copying everything down, because I will often say, this is the important part, you need to write this. Okay? Not always, but often. And then you can save yourself some time. But we're getting into this concept of density today. That's what you're taking notes on. And you're going to need to understand this. Not just, it's not just memorizing some facts. It's really, truly understanding a concept in order to do the homework assignment. And in order to do the upcoming lab that we're going to have. Call ahead up, please. Okay? So I did ask you to clear your desk of everything but your paper for notes and your pen or pencil. Try not to make this too terribly boring today. Let's see if we've accomplished something so far. Let's see if you already understand what mass is. Can someone give me a definition of mass? Alright, it is a cousin to weight, it is related to weight, but it isn't just how much something weighs. Yes?
How much space is in there?
Okay, I heard space. Who agrees with that definition, that mass has to do with space? Okay, I got a bunch. Who disagrees with that statement? That mass is about space? Liam, thank you for standing on your own. Right? It is Liam, right? Come on up. Another star for you. You have somebody anything? Keep them together, okay? Mass is not about the amount of space something takes up. What is that called? Marissa? What is the amount of space something takes up called? Volume. Can you point to the device in this room that we use to measure volume? We just did this yesterday, guys. Anywhere in the room? Pointing up here to one of these things. This measures volume? Yep, it does. Okay? And you read right off the side, right? Some of you did it like this, and that's why your readings were wrong. You forgot to put it on the table. So that's one device. Can someone name another device that measures volume? In this room. The balance thing measures volume. This device right here, that's what Chris is saying. Does this device measure volume? Does this device tell you how big something is? No. What other device measures volume? Paul? Yes, this is the device that measures mass. You're right. Which device measures volume?
The displacement jar.
Good. These little guys, the displacement jars, measure volume, right? So that's another kind. So you said one of these measures volume, those measure volume. There's a third thing that we used to measure volume yesterday. That would be these. Well, yeah, I mean, they have markings on the side. They're not very accurate. Huh? Math. You're right. Come get your star. Nobody could answer that first period. You guys forgot that you did this? Length times width times height? Doesn't this device tell you how big something is? Yes? Okay. So, we use these things to measure volume. Volume is about space. Did I care about how heavy those things were? Did it have anything to do with your number that you wrote down? No. Had nothing at all to do with it. Did I care about how big the object was for this? No. I only cared about how it went down compared to how these go down on the other side. I was comparing its mass to the mass of these three little weights here, okay? So this device, and there's a question about this on the homework, is called a triple beam balance. Repeat it.
Triple beam balance.
Not a scale, it's not a mass thingy, it's not the teeter-totter, okay? It is a triple beam balance or three beam balance. When I ask you on the homework today, what is the instrument called that measures mass, you will say triple beam balance. Good. So we know what mass is. Remember, mass has to do with what two things? Did anyone remember that from their notes? What determines an object's mass?
Gravity and weight.
Gravity and weight. No.
Number and size of particles in light.
Number and type. Number and type of particles found in the matter. Okay? That determines its mass. Then what gravity does to that mass determines the object's. The effect of gravity on mass is called its weight. That's the weight. Okay? What gravity does to the particles that make up your body, how it pushes you down, that's what we refer to as weight. Not exactly the same as mass. They are kind of related, but they're not the same, particularly when we get into different situations where gravity is different. All right. Now, based on your understanding so far, what would you say? We use the word dense or density. What would you say, Javier, is the definition for density? Can you use the word dense in a sentence? Any sentence. Doesn't have to be science. So what was dense? The book was dense. I think you said the poop was dense. Okay, that's an interesting sentence. The book was dense. Would you agree with that statement? The book is dense? Okay. That sounds all right. I'm not sure I fully understand that because the book can be described a lot of different ways. Anyone else want to take a shot at it? Give me another one that gives me a better understanding of it. Dense forest, which would mean what? Full of like green, Paula? Doesn't it also mean what? Okay, well, technically speaking, dense is like calling someone ignorant. And being ignorant and being dumb are two different things. Ignorant means you don't know anything about it. You ignore the information. Stupid means you're not very intelligent. Okay? You can be very intelligent and not know something about a certain subject. You see what I'm saying? Okay. So when the person is dense, head up, please. It means it's hard to get through to them. Like for some of you, you're being a little dense about mass. I've tried to explain this to you, and it's not getting through. Maybe I'm not doing a good job. I don't know which. Head up, please. So, I like that. I like the force one. That's a good one. Can someone tell me what we could do to change the density of this room? I'll give you a hint. About 3 minutes before you all came in here, the room was less dense. Fill it up with a bunch of stuff. What else?
Wait, you said you needed less things, right?
To make it more dense. If I said less, I meant more.
Yeah, like you said.
So fill it up. If I brought in Miss Salzman's class in here, what would happen to the density of this room? Head up, please. It would get higher or lower? Would it become more dense or less dense? More dense. So if I had twice as many people in here, it would be more crowded, right? If I took the same room and I reduced it in half, kept all of you in here and I reduced it in half, what would happen to our density? Would it go up or go down? Up. We would be more dense. How many think they understand this? Okay? Alright, I've got about 3/4 of it, so the rest I've got to get the rest of the way here. That's the concept of density. That's what we're going to be talking about. And this is such an important concept in science. If you get this, you can answer all sorts of questions. But right now, think of density as describing how crowded it is. Okay? If I'm talking about the density of people, I mean how many people in a certain space. Like in Tokyo, there's a lot of people in every mile of Tokyo. A lot more people in every mile of New York City than here. We say it's more dense. Population is more dense. Okay? So it's a good word not just in science but outside. But in science, man, it helps explain a lot of things. And I'm going to have you see if you can answer some questions to begin with here. All of these questions can be answered with your understanding of density. Okay? And I don't want you to answer out loud. These are just ones to think about, and then you can tell me later on what you think. Head up, please. Number one, what is the correct order of density for these balls? I have a little teeny tiny steel ball right here. You probably can't see that. I've got a rubber ball, a styrofoam, ping-pong, golf ball, ball of clay, steel wool, and then a large solid steel ball. And I want you to mentally predict which order these would go with, from more dense to least dense, most dense to least dense. If you understand what makes something more or less dense, you can answer that question. By the way, for future reference, when you come in here, I do lots of demos and I have stuff set up here. Don't touch the stuff on my table. Okay? You can screw things up. They are not hands-on things. The only time you ever touch anything up here is if I specifically told you can. Number two, some of you know a little bit about art and colors and so forth. Well, if I take these three substances, I've got alcohol that I have colored blue. Don't answer out loud. Yourself right now. I added a little blue food coloring to that. And then I've got vegetable oil. I kept its natural color. And then I added some red food coloring here to the glycerin. Okay? The question is, what will I get when I add those together in this graduated cylinder? Next question. How does a lava lamp work? You understand density. You can describe for me how a lava lamp works. Mine's not working too well. Number four, I've got a ring here and I've got a ball. And right now you can see that it definitely does not fit through there. The ball does not go through the ring. I want you to think of a method, a way that I could get that ball to fit through the ring without, head up please, without permanently changing either the ball or the ring. There is a way, okay? Finally, I've got a ball of clay, I've got a ball of steel. Predict, will the ball of clay float? Will the solid ball of steel float? Is there something you can change about the way they are that will allow them to float or not float, depending on what you predict? Okay. Again, understanding the density will help you answer all of those. Okay, so you ready for your first of I think maybe 3 or 4 mind-altering, mind-blowing statements. Science can do this once in a while. You can learn something in science that totally shocks and amazes you. It goes against what you think is going to be the case. It's just mind-blowing. Your cranium will literally explode and gray matter, brain matter will go flying all over the room when I tell you this next thing. Are you ready? Are you ready?
Yes.
Okay, I hope so. Don't be too afraid. Okay, here it is. Here's the statement. There's only like 3 of these that I say all year long, and this is one of the big ones. This is a big statement in science, an important thing. You are more not here than you are here. You wrap your brain around that. You are more not here than you are here. I'll put it in another form. You're full of holes. Or how about this? Maybe this will be easier for you to visualize. I could take you to one of those compactors that they use for cars, and if it was constructed in such a way that it could really mush things down small, I could take you and I could smush you down into a little cube this big. If I had enough force. Even smaller if I wanted to, but this will be fun. And that little cube would weigh the same as you weigh right now. You would have all your matter squeezed into that tiny little space. Okay? Weigh 120 pounds, whatever you weigh, and I can put you in my pocket. How cute. Look, I got a hobby. How cool is that? Right? Of course, I wouldn't be holding it between my thumb and my finger like that, right? Because it weighs 120 pounds. I would be able to hold it up. Now, that's not likely to happen because I don't have enough force or power here on the earth to do that. But, if what I'm saying is true, if you're more not here than you are here, You could walk through objects. You could walk through that wall, for instance. What I'm describing is the stuff that you're made up of, the matter you're made up of. The smallest little particles are called atoms. Okay, this should be review for you guys. Let's just see what you already know. This is a model, not a very accurate one, but a model of an atom. Atoms are made up of smaller particles called
Cells.
cells are made up of atoms. Atoms are made up of called and electrons. Okay? So this represents an atom. Protons, neutrons, and electrons. So what's all of this in between? Okay, the blue lines don't represent matter at all. They represent movement. But what's in here? Space. Just a lot of empty space. So all the matter that you're made up of, each little piece, each little atom is full of holes, space. And if I could get all of my little particles to line up with all the little holes in this door, I could walk right through. Seriously. So here's the door. The door is not solid. You think of it being solid, but it's not. It's full of holes. And you could walk right through it. You could get your matter, your atoms, to line up with those holes. The problem is that a lot of each atom is stuff that's in motion. It's not standing still. So it would be doing this. And that would be really hard to line that up now, wouldn't it? All of your atoms. But if you could walk right through things. Okay? To understand density, it's helpful to understand how dense you are. You're full of holes. I could squish you down and make those spaces smaller. I could squeeze the matter closer together. And there are actually 3 different forms that matter comes in. Actually 4, but for now we'll just say 3, because you've heard of these, I'm sure. 3 different states of matter. Who can name them? Solid, liquid, and gas. Now you should have already learned this previously, but if you didn't, this will be a helpful review. And I need 4 of you to help me demonstrate. So don't mind acting stupid. 1, 2, 3, 4. Good. Come on up. Alright. Each of you now are going to represent one of these. An atom. You think of yourself as being solid, but there's no space. But there is space. Okay? Little gaps and spaces throughout an atom. Each of you have spaces. Okay? And when you get together to form matter, you still have spaces. Get yourself in a circle. So we've got our atoms, A-T-O-M-S, all hooked together. I want you to grab 2 different hands. Just grab 2 different hands, or wrists. I don't care either one. 2 different hands. Well, that's lame. Okay. All right, hang on tight, because those represent bonds. You guys are held together by bonds. Now, atoms, like I said, they don't just sit there doing nothing. They're moving. So move a little bit. Come on, Adam. No, a little bit. Okay? You're kind of vibrating. Kind of vibrating in space. All right? Now, this is solid. This is solid matter. Your table, your desk, solid matter. You guys think of solid matter as having no spaces. Spaces. Lots and lots of spaces. Okay? Not only that, he's not solid. We call this matter solid, but it truly isn't. Let's say you guys could be a balloon. A latex balloon. That latex balloon can hold the helium inside. It can keep you from getting out for a while. But eventually, I'll squeeze through. And that balloon will sink down. It will lose gas. Now you think of a balloon as not letting anything out. Is that true? Of course not. Okay? Oh, we're all sweaty. Ooh, gross. Okay, wipe your hands off. Link up again. So they're solid right now. Now, even in a solid, there's vibration. So vibrate. Vibrate for me. Come on, you said you were going to play along. Vibrate for me. Now, I'm going to light a fire here, a small fire. It's getting a little hot. And my solid now will become, you skipped one, liquid. Let go of one hand. No, you got to be linked to somebody. You still have to be linked to somebody. No. Each person has to be linked to somebody. Okay. I'm very good at this. Here. Come over here. Okay. Here. There we go. Okay? This would be a better representation of what happens in a liquid. They're not as bonded together. They're not holding together as tightly. And now you can move around even more. Move around as much as you can and still hang on to each other. Okay? This is a liquid. You see them sloshing about? And what's got them, hold on, stop for a second. What's got them moving more is the heat here. You heated them up and they let go of one of those hands. And now they're sloshing about. Do it again. Sloshing about. Okay? Just one hand, not two. Just one hand. Okay. Now I light a bonfire underneath you. It's really hot. What are you going to do?
Run.
You got it. Drop all your hands, break your bonds, and run away. You want to get as far away from each other as possible. You want to get as far away from this heat source as possible. As far away from the heat source as possible. And you're still doing the hot dance. Do the hot dance. Hop, 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 hop. Come on, you said you were going to play along. Hot dance. Hop, 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 hop. No hands? I don't get hands? Hot dance.
I'm going with Myers.
There you go. Thank you. Okay? Now, this is what happens in what state of matter?
Gas.
A gas. This is why the gas expands. And this is why it pushes on the balloon, because it wants to spread out as far as possible. Now, these little examples might seem stupid to you, but when I ask you questions later on, if you visualize what happened here, you can answer some basic questions. Let's try this. You guys can sit down. Thank you for your help. Question number 1. Which state of matter is most dense?
Solid.
Solid. Which is least dense? Gas. What did I add to increase their density? Or to add to decrease their density?
Heat.
Heat. When you add heat, they spread apart. Now, did I change the number of atoms? No. The number of atoms stayed the same. But when they spread apart, I increased the... No, I didn't increase the density. I increased what?
Space.
What do we call the space, guys? Volume. Okay? You see that? When they spread apart, I increased the volume. They took up more space. And when I cool them down, they come back together and take up less space. So heat them up, they expand. And we would say they are less dense. Okay? How many think they understand this density thing? So if I were to double the number of students in this room right now, what would happen to the density? It would increase. Okay? What would happen to the mass? Would it go up or down? Up. I added a bunch more stuff. We call them people, right? And I increased the mass. If I double the size of this room, I have doubled its volume. What have I done to the density? It went down. It's less crowded. Okay? So understanding matter is real important. Solid, liquid, gas. If you change the temperature, things are going to spread out more. Okay? If you add temperature, add heat to it, they're going to spread out. All right. And that's all this little simulation is trying to show. It's not that great, but might help some of you that didn't get it already. You can see here that we start with water. Like when you guys were all held together, maybe I turned you into ice. Boom. You lock together and hold each other tight. Now this shows no movement, which isn't exactly accurate. If I get you to absolute zero, then it would be. If I increase the temperature, now you're going to be moving around. You're sloshing around, but you're still hanging on, okay? So liquid. As I increase the temperature further, your motion gets greater and greater, and little atoms actually escape. We call that evaporation. Okay, as the temperature goes up, they escape. When we get to that special point called the boiling point, they really start escaping rapidly, and you can see how much space now. They've really spread out from one another. They're trying to get away from each other, and we now have a gas. All three states were all water. What we did is by adding temperature, we changed the density. The more heat we add, the more they're going to want to spread out. Okay? All right. Now, I'd like a volunteer to come up here and put these in the correct order. Since this is hard to see, I did it up here. You want to do this, Michael? Okay, hold on. Before you come up, let me just show, since you've been doing this all year long, this kind of thing. If you want to move things around on the board, you can drag them. Just keep your finger firmly on the board. Or you can do this. Touch the object, touch where you want it to go, and let go of your original hand. Okay? Touch, touch, release. Touch the object, touch where you want to go, and let go of your original hand. What I want you to do, Michael, and you're going to probably have to stagger up and down, is put the most dense down on this end and the least on this end. Come on up. Let's see if you guys agree with what he thinks. So we want the most dense on the left. I'm going to need you to speed up a little bit. Just go ahead and make a guess and done. Okay, so it goes styrofoam, rubber ball, golf ball, and so on. Anyone agree with that order? Nope? Go ahead, have a seat. What do you think should be on the far left? Alexis? The little steel ball should be the most dense. What do you think should be on the far right then? The steel wool. Okay. Anyone else have a different opinion on the far right? You need to sit down. Because it's hollow. Okay. Interesting. What do you think? Styrofoam ball? Alright, let me show you the order. You might notice that I have my own little cheat sheet here. Because the truth is you can't know the density of an object just by looking at it. Some of these you can take a pretty good guess at because you know what kind of stuff goes into it. Which is more dense? I've given you a copper cube and I've given you a wood block. You just knew that, right? Is she right? Copper cube's more dense than this one? Yes. And that you can tell because they both have the same what? Not shape, but size. They both have the same volume. But this one has more stuff packed into it. It's like adding people to this room. When I added people to the room, did I change the size of the room? No. All I did is add stuff. So this has more stuff packed into that same amount of space. Head up. So the volume is the same, but the mass is different. This has more stuff. So this is more dense. If everything were the same size, that would be easy to know volume. You can hold it in your hand and know. But because you can't know volume or know density just by knowing the volume, you need to measure. You need to do two things. That's why we learned how to find mass last week and why we've been working on volume this week as well. Because until you can find both of those, you can't know density. I have to actually measure both things, and then I can determine its density. How much stuff is packed in how much space, okay? Just because something's big does not make it dense. Just because something's small does not make it dense. Just because something weighs a lot doesn't make it dense. You have to know both pieces. And the most dense thing up here, what do you think it is? Steel ball. But Alexis said she thought the little one, which I kind of like because a lot of people don't think, the little one goes down here. A lot of times people will put all the balls lined up from biggest to smallest. That's not density, that's volume. Both of these have the same density. You know why? Because this is a solid steel ball and this is a solid steel ball. They're made of the same material, they're solid steel, they have the same density. Just because something's big doesn't make it more dense than something that's small. You have to know two things, the mass and the volume in order to find that. Next comes play. You're right. After that, ooh, you're good. Golf ball after that. I'm good. After that,
Ping-Pong. No steel wool.
steel wool. Yep. Then ping pong ball is the least dense. I don't know how many of you predicted that, but it is the least dense. And styrofoam comes before that. Okay. Why is the ping pong ball less dense than the styrofoam ball?
Because it's not filled up. There's nothing.
Well, it is filled up with something. What's it filled up with?
Air.
Air, which is a gas. And we all know a gas has stuff that's really spread out. The styrofoam ball has some air in the little pockets, but it also has more matter in that amount of space. So this is more dense than the ping pong ball. Now the thing that might throw you is the steel wool. Steel wool is steel, this is steel. How come this is less dense than this? Yeah?
It has little holes in it.
Yeah, little pockets. And again, what's in those little pockets? Air. Okay? So do you think that this steel ball will float?
No.
No. Do you think that this ball of clay will float?
No.
No. Okay? It's more dense than water. That's why things float or sink in water. It has nothing to do with just how heavy they are. A big steel cruise ship is going to be a lot heavier than, a styrofoam ball, for instance. But they both can float because they are less dense than water. Will this little teeny tiny steel ball float? No. Sink straight to the bottom, just as quickly as the big one did. Okay? So it's about density. Density lets me know whether or not things will float or sink. And again, remember that density is not something that you can determine just by holding it in your hand. Density is not about how something feels. Head up, Alexis. If you take, say, this rubber ball and this clay, which do you think is more dense again? It is right there. Okay, the rubber ball. The clay. The clay is more dense than the rubber ball, but it's mushier, softer. Shouldn't that be less dense? It's not about how hard or soft something is. It's not about how much it weighs. It's not about just its volume. It's about all of those, or both of those things, volume and mass. This is the formula for density. In order to find the density of these objects, you can't just hold them in your hand and feel them. You have to actually measure two things. You have to find the object's mass and its volume. You measure its mass in what units? What do we measure mass in? Grams. What do we measure volume in? Well, that's the base unit, but what do we do in this class?
Meters.
Huh?
Meters.
Well, that's the base unit, but what do we do in this class, in the labs?
No, like.
A liter's a pretty big thing compared to a little gram. Milliliters, guys. We measure the volume in milliliters. So that means that you then, if you want to find the density of this clay, you would take it over to the triple beam balance. You find its mass. That number would be so many grams. And then you divide that number by its volume. Maybe use the displacement jar to see how much water it pushes out of the way. Okay? It's grams divided by milliliters. So I'm going to give you some simple math like this to do on the homework. You're going to be given a mass in grams and a volume in milliliters. Which of these is more dense? The first example or the second? I got a mass of 10, a volume of 2, a mass of 20, a volume of 4. Second one's more dense? Here's the formula, guys. They're the same. What's the density of this one? 5. What's the density of this one? 5. And this seems to throw a lot of people because they don't understand that density is about two things. It's not just about its mass. It's not just about its volume. It's both. This, yes, it's twice as much mass as that one. Twice as much stuff. Okay? But it's also twice as much space. Takes up twice as much space. If I were to double the size of this room and double the number of people in here, would it be more or less crowded? Same. I doubled the mass and I doubled the space. So the density is the same. Okay? And you might notice that this large steel ball versus the little steel ball, they have the same density. I showed that on the previous slide. They're both solid steel. It doesn't matter that one's big and one's little. If they're made out of a pure substance, steel, they're both going to have the same density. Okay? And they both will sink over there. The label again on this came from taking a mass number in grams and dividing it by a milliliters, a volume number in milliliters. So your label on your answer is going to be G/ml, because that means grams divided by milliliters, which is exactly what you did here. So when you label your density answers, it's going to be G/ml. Everybody got that? If you found the volume in centimeters cubed, which you will for some of the homework, then your label will be what? What? Okay, guys. This was grams per milliliter, right? Because we measured this in grams and this in milliliters. So that's the label we put on our answer. But what if we measure this in centimeters cubed? You got it. G/centimeters cubed. Okay? If we measure it with a ruler, we do it grams per centimeter cubed. Alright? So again, density tells you a lot. Density will tell you what will float versus what will sink. You learned a little bit about water already. On one of the labs, I had you measure out 30 milliliters of water. Do you remember that? And then tell me what the mass was. How much mass does 30 milliliters of water have? How much mass? 30 grams. How much mass does 60 milliliters of water have? 60 grams. Put your head up again. How much mass does 100 milliliters of water have? 100 grams. How much space will 10 grams of water take up? No, that's not space. 10 milliliters. So what is the density of water? If 30 milliliters weigh 30 grams, 100 milliliters weigh 100 grams, what's the density of water? 1. That means every milliliter of water weighs 1 gram. That means the density of this tiny little drop of water is 1. The density of this tub of water is 1. The density of a whole pool of water is 1. If the object sinks in that water, what do you think? Is it more or less dense than the water? More dense. The clay sinks to the bottom. It is more dense than water. Could I change it in some way to make it float? This was one of the questions I asked at the beginning. Could I change that clay in some way to make it float? What do they make big ships out of? Steel. Can you make steel float? How? Make it hollow. So if I take the same amount of mass and I spread it out and make a giant ball out of it that's filled with air, now it will float, right? So I didn't change its mass. What did I change? Its volume. Good. Don't just say shape. It's volume, the amount of space it takes up. So the lower the volume, the higher the volume is, the less dense it's going to be. Here's that same amount of clay now, but shaped into a tray. What's going to fill this space? Air. And we all know air will float in water. If you go to the bottom of a pool and blow out air bubbles, they'll come to the top. That's why they float. That clay, I haven't changed its mass. Same stuff. All I've done is spread it out over a larger space, and now it can float. You do the same thing with blocks of steel. You put a beam of steel into the ocean, straight to the bottom. You spread it out and make a big open space out of it, where the air can go, and now it floats. Yes?
How come the blocks when you do that float?
Because the material they're made from, wood, is less dense than the water, and it floats. So a wood boat by itself is hard to sink if it's made out of the right wood and you don't have a lot of other stuff sitting on top of it. Okay? But there are some kinds of wood, by the way, that are more dense than water, that won't float in water unless you have a lot of extra air. Good question. Okay? Remember, even things that we think of as solids like these, there are little spaces in there. Okay? So when something floats, it tells us that it is less dense than the stuff that it's floating in. Which has a higher density, 1 milliliter of water or 1 million milliliters of water? Which has a higher density? Neither. Who said that? Good. They have the same density. What is it? 1. Okay, we add more water, we add more mass, but we also have more space. It's the same volume. So I can actually take a whole bunch of salt and pour salt in this water. What will happen to the density? The salt will dissolve and the water level won't go up. So what happens to the density of the water? It's higher. Salt water, ocean water, is 1.4 grams per milliliter. That's why you float better in the ocean than you do in your backyard pool, because of the salt. Okay? The density determines that. Now, if I add these three together into one graduated cylinder, what am I going to get? A little red. Patriotic. Here's a little white. This is the same thing you guys experienced with salad dressing. Here's a little blue. Each of these substances has a different what?
Density.
Density. The least dense substance is what? The alcohol. The alcohol I colored blue. The least dense one is on the top. The most dense is glycerin on the bottom, which I made red. Okay? And that's the same reason that the oil and vinegar and water, they separate out into layers. Head up, please. It's because of density. Okay? And in fact, in this tube, I have stuff that's floating at the top, I have stuff that's floating in the middle, and stuff that isn't floating at all on the bottom, because of the density. This little white thing, piece of plastic, is less dense than the green stuff. Okay? But it's more dense than the piece of rubber, which floats at the top. Okay? When you have an oil spill in the ocean, where does the oil go? To the top of the water. What's more dense, water or oil? Water. But oil feels more dense, doesn't it? Feels thicker. It's not about how it feels. It's about weight, or mass, I'm sorry, and volume. Yes?
How the law works?
Well, why don't you tell me, how does the law of Length work? Explain, just talk me through it here real quick. Paula?
It's like the stuff inside, like it's matter, it's like whatever, it's a lot less dense than the water inside.
Okay, so when the lava lamp is off, this wax, basically what it is, sits on the bottom, right? It's more dense than the liquid. Then,
And that's because it heats up.
okay, so you heat it up and the wax does what?
It forms into like a weird shape.
Well, what happens to the volume of the wax when you heat it up? Yeah, it increases. Good. It expands. You guys do understand that. When you heat things up, they expand. Yes? Okay. So when I heat up that wax, it expands. Its volume goes up. What happens to its density? Does it become more or less dense? Less dense. Exactly. Which allows it to float. So it goes to the top, and it's all happy and it floats, but then it's away from the hot light bulb, and it starts to cool down. And when it cools down, what happens next? It sinks, because it becomes more dense. So what's happening there when you watch those globs go up in the lava lamp is each glob gets less dense, rises, more dense, sinks. Less dense, rises, more dense, sinks. They're changing the volume. I haven't changed what's inside that. You're using heat to change the volume. And you saw that over here with my atoms. I changed your volume, how much space you took up by adding or taking away heat. How can I get the ball to go into the ring without changing it permanently?
Makes them
I just do this. I just put it right through. Okay. You're sitting in front of you the whole time. Now it goes through just fine. Here's my secret. The ice is already melted, but I had ice water. This was resting in the ice water. Cold makes things contract, get smaller. Okay? Heat makes things expand. I have a hot plate down here that this was sitting on at 600 degrees. So temporarily, this ball actually got bigger. This ring actually got smaller. Then I showed you, and they wouldn't fit, right? Then I let them sit there, and both of them now have reached room temperature, so now the ball does go through the ring. It's all about density. I made this more or less dense, and I made this one more dense by changing the temperature. So this whole thing of density has a lot to do with science. It explains a great deal. Now, I'm going to have you pick these up on the way out, because I know if I give it to you now, hold on, if I give them to you now, you're going to pack up and not listen to me. I want to point out a few things. On this first section, there's 6 questions. Don't forget to put the label. And because your volume was given in centimeters cubed, and your mass in grams, what's the label going to be? G/centimeters cubed. You got it, okay? Then, so make sure you put that correct label on there. Also, make sure that you round off to the hundredths place. When you do your division, round off to the hundredths place. That'd be like 0.01. Okay, I'll wait till you're done. I know the bell's gonna ring, guys, but I need to finish. There's a question here where you know the answer. It has to do with that guy over there. We've mentioned several times. And then there's another question about a box of sand. And there's actually 3 separate questions on that box of sand. And we take that box of sand and we add water to it. It's still the same size box, but we've increased its density. And then we cut that box in half, and it's still a box of sand with water. It's still wet sand, and I ask you some more questions about it here. When you get to the one about the box of feathers and the block of lead, be careful. Think about it before you answer. Pick this up on your way out. I'll see you tomorrow. You can go.